Hello, and welcome to the first episode of our April live streaming series, where we are going to talk about physical AI with NVIDIA and AWS, and I'm very excited with that. We are going to do 5 episodes in this matter, and that's a perfect coincidence because the complete stack for physical AI, as you're going to see along this episode, is made of data, training, simulation, sim to real, and agentic orchestration. So, our goal is to divide each of the aspects of this stack into 5 different live streaming episodes for you every week of April in the same time slot. My name is Raf Lopez, and I will be the host for this series. Also on camera and doing awesome presentations, demos, commentaries, and answering your questions, we will have subject matter experts from the AWS Solutions Architecture team and folks from the NVIDIA Developer Relations team. Now, I must say, I'm also new to this topic they are going to present, so please bring your questions to the chat. I would also like to remember that this is supposed to be an interactive session, so bring your questions to the chat. And we also have both AWS and NVIDIA staff looking for your questions right in the chat. So please, again, I beg you, this is an interactive session, so do bring your questions to the chat, and I will highlight them in the video and show for everyone. I am excited for this, and I have the pleasure of receiving people from AWS and NVIDIA in this show. So let's start with a round of introduction for today's episode, so everybody meets everybody. Should we go in alphabetical order? So Brett from NVIDIA.
Yep. Hi, folks. I'm Brett Hamilton. I look after developer relations for Cosmos, our World Foundation Model platform at NVIDIA. So been looking after visual AI here. In a prior life, was on the language side of AI, LLMs, and what we used to call chatbots.
Thank you. Thank you very much for coming, Brad. You that are on the chat, please also let us know where you're watching us from. The next one that we see on the screen is Najma from the AWS Solutions Architecture team. Welcome to the show, Najma.
Hey everyone, my name is Najma Rahman. I'm a solutions architect here at AWS, and I'm specializing in physical AI. So I've had a chance the last few months to start getting into some of the Cosmos models and exploring that. So excited to be talking about that with you guys today.
Awesome. And we also have Super Sean from AWS Solutions Architecture team.
Hi, I'm Sean Kirby, and I'm a cloud architect in our AWS Professional Services organization. And I work with customers from early stages of understanding their business opportunities and challenges right on through architecting and implementing solutions, including more and more physical AI. So great to see everyone here today. And with that, let's dive right in. So as Raf was saying, this is the first in our 5-part series, and we wanted to give a level set because these 5 pillars that we're going to be talking about over the next week are really new and cutting edge, but we wanted to give our definition of physical AI here because it's really very broad in what it covers. Basically speaking, physical AI is the embodiment of artificial intelligence in all kinds of smart objects. And while most of us might think of robots as one example, it's certainly one of the best examples. It's not the only by any means. Self-driving cars, autonomous vehicles for moving equipment and products around in warehouses and factories is another example. Or even an entire factory production line or the whole factory itself. In fact, even large-scale smart systems like entire smart cities could be considered physical AI solutions. And well, what makes all this possible? In a nutshell, it's much of the same magic that we saw with generative AI through things like large language models. But in the case of physical AI, it incorporates many more different types of inputs. So in addition to the verbal inputs like instructions about what you want the smart object to do, there are numerous new sensor inputs as well. This is multimodal. So things like video or telemetry from a sense of touch, temperature, humidity, any kind of information about the physical world. And it's all fed into these intelligent models. And out of that come instructions for the smart objects to take action and do useful things. So this is not, of course, some pipe dream or something way into the future. It's been around for some time now, and we wanted to give you a couple of examples of this in action. At Amazon, we use this a lot in our warehousing and fulfillment centers. This is an example of our Vulcan robot that helps people to pick items from racks or to stow items, and it focuses on the very highest and the lowest parts of those racks. So it relieves people from the need for bending down low or climbing up and down ladders. It can save them as much as 90 minutes a day. And it does so not only through video, but also through some haptic sensory input and force feedback, so that it can place objects, move objects out of the way, and place objects very accurately. Another example that we use as well here in Amazon is for testing our products. As we're coming out with new products, they have new packaging and they require different ways of manipulating them in order to inspect them for quality. We're going to be talking a lot about synthetic data generation today. It's really the first of the 5 pillars, and we use a lot of that here. We take the CAD specifications for the packaging, and through the tools we're going to be talking about, we generate 50,000 variations of that, and we train a robotic arm to learn how to manipulate that new product and inspect it for quality assurance. And this allows us to employ a zero-shot application, so we don't have to stop our production lines at all. We can deploy that trained software from simulation, which we're going to be talking about in an upcoming week episode here this month as well. We can deploy that directly to the robot arm, and then it knows immediately how to inspect that new product. And we can even use Bedrock in the background with some models to further analyze the designs of that product and know exactly what kind of testing it needs to do. So a lot of physical AI there in some very basic quality assurance applications. Well, what does it take to achieve all of this great new capability from physical AI? We believe 5 things are essential, and we're starting with data today because it's often the first place that organizations start implementing new physical AI solutions, and that's acquiring large quantities of high quality data. We then use that data in training to make models smarter, fine tuning. It could be imitation learning or reinforcement learning, lots of different types of training we're going to talk about next week. And then simulation. So once those models are trained, we simulate in photorealistic worlds with real physics to see how they'll behave before we even get to an actual real world test. That's what we do in sim to real. And then once we have a good model working for some simple actions, we can string them all together to create more complex behaviors. And this is through agentic orchestration, or the 5th pillar that we'll talk about last. This is certainly not without challenges. And one of the biggest is just getting a hold of enough data of a high enough quality to do good training or even good simulation. And we're going to talk a lot about how you can do that today and really multiply your assets quickly to achieve this objective. Some of the things we'll talk about in the rest of the series include simulation accuracy. If you don't have an accurate model, you can do tons of great simulation, but then when you transfer it to the real world, it may not work at all. We'll tell you how to overcome that. And then all of these stages require pretty sophisticated tools, as you might imagine, to design and develop these solutions. And they have complex setups. So we're going to show you starting today with setting up some of the very sophisticated tools for data generation, how you can do that quickly, easily, and repeatably so that you can collaborate. Time to results, right? It's extremely competitive, extremely fast-paced time in our industry with physical AI. And if you're training on a single instance, it can take days or weeks or even months to train a good model. So we're going to show you in a future session how to do that in parallel and also very cost effectively. And then last but not least, when you get to whole systems of smart objects like factories or cities, just orchestrating them and deploying all of your different models to different types of hardware requires management at a level where fleet management becomes really challenging. And we're going to show you how to do that as well in part of the agentic orchestration talk. So some of the technologies we'll be covering in these 5 pillars. Again, today we're going to be focusing on the data and synthetic data generation. You'll learn about NVIDIA Cosmos and World Foundation models and how you can run those on our Elastic Kubernetes service, EKS. the future, we'll talk about training, Isaac Lab and AWS Batch, some Isaac Sim, and even just Elastic Compute Cloud, some of the tips and tricks for using that to scale your simulations cost effectively. And then
Nice.
at the end,
I see a question on the chat here. What is the
yeah,
scene to real thing I see on the slide? Are you going to talk about that too? The answer is yes. And coincidentally, as I said in the intro, the stack for physical AI in NVIDIA is divided into 5 pillars. And guess how many weeks do we have in April? Five Wednesdays. So today we are talking about the first pillar, data. But in the episode number 4, we are going to cover the scene to real.
absolutely.
And we have
Yep.
Greengrass. We have fans of the AWS Greengrass service. It's a very cool IoT service, also one of my favorites. We have people from Mumbai watching us. And how long this will be, someone already kindly answered that. It's going to last for 1 hour. So we are running the show for 1 hour, and we are 12 minutes in. So stay with us. We have lots of contents to cover. Sorry, Sean, for interjecting. I'm going to do some of these interjections with questions from the chat, and keep bringing the questions, everyone.
Great stuff. Thanks for the enthusiasm for Greengrass. That's a favorite of mine as well.
Yeah.
So let's transition into the focus for today around data. And just to go one click deeper into the problem here, as you're well aware, for more traditional AI, we have tons of data from the internet, right, for training the language models. But for physical AI, we're really in the stage of creating that. We don't have a whole lot of those kinds of sophisticated robot videos. So we can do things through remote teleoperation and so forth with motion capture, et cetera. But that doesn't scale. It's hard to do, and it takes a lot of time. So what we're going to talk to you today about is bridging that gap and extending and multiplying a little bit of high quality data with some instructions to produce a large quantity of realistic and high quality data so that you can really accelerate your physical AI program. So without further ado, I'm going to hand over to Brett, who's going to dive into some of the technologies to help you there.
Cool. Thanks, Sean. So yes, as we bring up the screen, yeah, I'm going to talk about the challenges that we'll have in the areas of data. So what's the challenge that we'll have for physical AI? What we're doing in Cosmos to help to address some of those challenges. We're going to look at some developer workflows that you are going through or will go through for physical AI, and look at some examples, and then I'll pass to Nejma for a demo and some other content as well. So anywho, so the challenge in physical AI is around the big data gap, as you see in the chart here. So looking across here, unlike with LLMs where we can train those systems based on internet data, only a small portion of internet videos are usable for training physical AI systems. And so as Sean was saying, we can augment that with human demonstration like teleop, but that still leaves a big gap, and that's the synthetic data bubble you see on the chart. And so that's where we're focused. That's what the content is all about today. So so that also was a part of the genesis of the development of Cosmos. So a World Foundation model platform for those who aren't yet familiar. There's 3 model families for Cosmos. Predict is, as it says, it will generate future worlds based on image and text and video inputs. So it will produce up to 30-second videos that can be used for downstream policy evaluation and model training. Cosmos Transfer is some people call it a style transfer model. So you can use the controls that are available in the model for segmentation, depth, blur, and edges to control an output and do transfer style onto a single video and create many different variations of that. And that's a big portion of what we're talking about today in multiplying and scaling data. And then Cosmos Reason is our vision language model, a VLM, purpose-built for physical AI. It does chain of thought reasoning. And so those are the 3 model families. I'm going to just quickly zoom out a little bit. Cosmos is also a platform of capabilities for developers. So super brief, I talked about the models in the upper left there. Research is working on Cosmos 3 right now, so quite a bit of velocity and focus on Cosmos. So you'll continue to see those new models and new checkpoints available. Cosmos 3, think summerish for at least for US or the Northern Hemisphere. Also, open data sets. So we've open sourced about 15 terabytes of physical AI data sets in our Hugging Face repo, over 300,000 trajectories, and then 1,000 USD assets. So USD is super critical for the physical AI ecosystem. So we're trying to help unlock. We've also got a lot of ISV partners that are building USD libraries or marketplaces of their own to help developers in that sense. So, and then frameworks, Cosmos RL, Sean talked about reinforcement learning. That's what that is. Cosmos Evaluator is new and was announced a couple weeks ago at our GTC conference. We're going to talk about Cosmos Evaluator a lot today as well. I'll come back to that. And then we have these things called blueprints. And so sort of reference architectures, if you like. VSS is for visual search and summarization, very popular blueprint for all kinds of computer vision pipelines and applications. These are all open source, and in the case of the models, open weight. They're number one in terms of open models on the physical AI bench, and then about 14 months in, a little over 6 million downloads, which is pretty good for a purpose-built model such as Cosmos. So back to the challenge around data. So we know from talking to developers that whether you're in one of these phases of a physical AI development, from data generation through to simulation and deployment and an embodiment, there's friction within those phases, but there's also friction stringing these things together. And so we're working on capabilities to address both. More specifically, those key areas of friction, on the left, addressing data scarcity, in particular domains. That's what we'll talk about today. How to scale those things, or to multiply that data, to do it quickly and more cost effectively. We have a library called Cosmos Curator as well that helps to do data selection or curate video libraries for model training. And so that helps with what was heretofore very manual and tedious process for data selection. And then a way to integrate, as I say, the components and orchestrate them. And so to build a means for scale and velocity, to build SDG or scaling data, and make that applicable to all domains. So we're going to get to some more visuals straight after this, but you got to hang with me just for the for the architecture. So what we also announced a couple weeks ago at GTC is a reference architecture called the Physical AI Data Factory. And so think of Data Factory, it's exactly what we're talking about today, scaling data with NVIDIA in your AWS environment. So starting upper left, you're generating data through cameras, human demonstration, embodied sensors, radar, LiDAR, etc. You may be augmenting that with NVIDIA NeuRec, also a new capability, and NVIDIA Omniverse for 3D ground truth data. And then you get a video data library, the first orange database there. That's where Cosmos Curator comes in. I want to curate the appropriate parts of the video and split and chunk and deduplicate all those videos. That's what Cosmos Curator does, and gives you the captioning and embeddings that are needed. Then going to augment that data. That's where Cosmos Transfer comes in. So we're going to create many different variations of the ground truth that you like. And then you're going to need to evaluate it. So of all that data, is it useful for training or is it not? That is the purpose of Cosmos Evaluator on the right-hand side, and you end up with an augmented and graded data set and a report to tell you about what happened.
That's cool. There is a question here from the chat that asks, are the Cosmos models on Bedrock and SageMaker, or you need to self-host?
Yeah, so Nejma will talk about that specifically. You can run those in your EKS environment in SageMaker Jumpstart, talking with the team about Bedrock, not available yet for serverless, but as that is something that we're looking at.
Yeah, I think that someone from NVIDIA was monitoring the chat and answered that is a multi-model foundational model, such as a VLM that is trained for physical AI applications, and you can run Cosmos WFM on AWS. There is a link that people can click on the chat. And last but not least, someone gracefully said that Cosmos is available on SageMaker and AKS. So thanks a lot for that.
That was a much faster answer than mine.
Yeah, it's so easy to do this show when we have experts monitoring the chat, and I just bring their answers. That's awesome.
Yes. Done.
Great. Yeah.
Okay. Anything else, Ralph?
No, the chat for the chat, someone said that they're familiar with foundation models, but world foundation models is new to them, which is interesting.
Yeah. So without getting too far off topic, there world foundation models is a pretty popular area. This is where we're training models, foundation models, to be able to simulate the real world, so they understand the physics and physical capabilities of the real world, in addition to just language and things that LLMs understand. So think like digital to physical, and world model is generally understanding the physical.
Cool. Yeah.
It's early days, and you'll see a lot more world models.
Mm-hmm.
Okay, and so as Ralph said, in the middle layer here, these are all topics that we're going to cover, that AWS and team will cover in upcoming Wednesdays in this series, like fine-tuning, I think is next. SIL testing, simulation, sim to real deployment. And then the lower level, orchestration, that's super important. NVIDIA Osmo is what is referenced here, and that's will also be covered in I think the last Wednesday. So stay tuned for those sessions. And this is intended to be applicable to all the physical AI domains that are listed along the bottom. Mm-hmm. I think I'm going to keep going in the interest of time here. Yeah. So this chart, we kind of covered most of this. Let me just maybe say, I think Nejma is going to cover compute and data services and the core cloud services in the gray box. Of course, this all runs in your AWS environment. So let's come back to that and how to make it, make all this come together and make it work. I'm going to play just a quick video on how this can all come together in sort of an agentic view. So take a look real quick, and I'll pause. And there's no audio, so you're not missing anything.
All right. If you want to talk over it,
Yeah, it's quick. So I was trying to let people focus on this. But what you're seeing is
that's cool.
Yeah, so the developer giving a single video to Claude, who's able to go invoke that pipeline that we just looked at. It was just an agentic work through of that pipeline. So to say, I need multiple copies, augmentations of that video. I need to know, generate the types of multiple choice questions to show whether it is those augmentations are valid or not, and if they're usable, and then presenting the answer at the end. So this is kind of where things are headed, and we think this is obviously a good way to scale. I think this discussion is all about scaling. So just wanted to show sort of a to-be state and something that we want to work towards. Here is an end-to-end video for the physical AI data factory. So again, think from input to understanding, annotation, augmentation, and evaluation here. And so there's two scenes, a pedestrian in a piazza and an AMR in a warehouse setting. And again, generating augmentations, that's Cosmos Transfer and Cosmos Evaluator presenting multiple choice questions to be able to grade those augmentations. Are they useful? Are they valid? And then this is the report sort of that we were talking about at the end. And what are the model artifacts used in this workflow? You can see those on the bottom. So these are just some examples of the workflow. The augmentation or the multiplication of these video scenes is a key part of the pipeline. And so I mentioned Cosmos Transfer. So its role is to take a video input and then to augment that according to the series of controls that you can configure. But we can also help to, what the reference architecture does is to help make a consistent or programmatic approach to do this, invoking the LLM and just providing user configurable parameters, in this case for weather, road condition, and time of day down at the bottom there. And I guess the video didn't run. So that as you go through an initial set of augmentations or a follow-on set, that you get consistent control of the video, but also then augment the components that you want. And so you can see here you're getting different weather, road conditions, and time of day. So that's what the data augmentation is all about.
That's very interesting. The way so I live in Manhattan, like I live in New York, and you know how sometimes the traffic signs are not synchronized, and then like the light opens and you walk and then dang, it's closed. So I'm assuming that you could have a camera and on streets, and then you can do some type of analysis to detect when signals, when like semaphores, they run out of sync, for example. Would that be a use case for that?
Yeah, so where the Cosmos Reason model is a world understanding. So we'll take a video as input and then reason through that video, that chain of thought reasoning. That's probably a use case for Cosmos Reason, Raf.
Interesting, I see.
Totally valid. You may be augmenting that, you may not. But the first or the most obvious use case for something like that, I'd be able to reason through what is happening when the lights go out of sync.
To detect if the signals are out of sync or something like that, based on the flow of the cars, and that's cool.
Yeah, exactly. Okay, stepping forward. So I mentioned Cosmos Evaluator. This is a new capability, and it is doing data grading as the title suggests. And so comparing this, our AV team compared this with manual data validation. Our customers gave an average of roughly 3 minutes per clip, per short clip. So multiply that times the thousands of clips that would be required to do model training, plus the deviation for human validation, means that that's timely and less valuable overall. So the point of Cosmos Evaluator will be that first step to automating data evaluations using Gen AI, and then deterministic checkers underneath for specific parameters. And you can determine what those grading criteria are. So here in the video, you'll see Evaluator grading for hallucination, here object tracking, and then it will invoke a VLM checker right here, I think coming up in the screen. So there it is, the VLM sort of reasoning through the video and doing its own check. So that's a look at evaluation. And now we want to put these things together. So the power of this this reference architecture, the physical AI data factory, is the loop between Cosmos Transfer, Cosmos Evaluator. So I can, in this case, take a traffic scene, an input on the left, use Cosmos Transfer to generate photorealistic variants of that scene on the right, and then run that through and compare that against the multiple choice questions here. For the augmented video, was there a violation? Yes. And what type of violation? That was a red light violation, and it caused an accident. So presumably that's something we want. That's the condition we want. So that goes into the training database. If you don't get that, it just goes back to transfer to do further augmentations, and you run that loop. And that's the objective is to scale the data augmentation in this manner. So a couple examples I'll run through real quick, and then we'll go over to the demo with Nejma. Here's targeted augmentation in the case of robot nav. So again, you set the conditions for, in this case, lighting and floor color. Do I have to cut? Yeah, I got to cut through here. So so these videos on the left pass the hallucination checker and attributes. The ones on the right, the top one you saw a hallucination with the lighting, but then the other attributes are passed. So this is how the augmentation evaluation works in concert.
Nice.
Here's another. Oh, yeah, go for it, Ralph.
That's interesting. Someone just asked, is that how the Cosmos Evaluator catch potential hallucinations? And that's what you're showing.
Yes, yeah, exactly. So I'll show another example of that for an AMR in the warehouse scene, another AMR in the warehouse scene. So you set the number of augmentations desired. So here 5. The parameters, in this case, the floor color, lighting conditions, wall color. And here, the evaluator is indicating that all the attribute checks are passed. So that's that example. Here's another one for robot brain fine-tuning in a perception in a factory warehouse setting. Sorry, I'll pause it because it kind of goes quick. So of the 3 augmentations, the first 2 pass, and the third one asks for this lighting condition of sodium, and it fails that. So that would go back, regenerate another video where the lighting is sodium, and it passes. So again, just sort of multiple examples for slightly different domains. Here's one final one. And so this is a input of a traffic scene similar to what we were looking at before. And here's a failed augmentation. We asked for a time of day, which was night. And I think this is sunrise or sunset. So sends it back for another variation where this is a nighttime scene. And then those checks are passed. So just wanted to share some examples there. And so I think last one, and I'll pass it over to Nejma. Here's some examples of use cases. If you want to try these, some good use cases for the physical AI data factory, from perception to outdoor and indoor nav, gross manipulation. I won't read through all this, but you can see good source data sources for starting with those capabilities. So we'll have those as leave behind, so you can read through this. And And I think that's it. Yeah. So pausing.
Cool.
Yeah.
Yeah. There is a question on the chat here from Kevin Mayers. Thanks for the question, Kevin or Kevin. Let me know if I am saying your name wrong. What is the average latency from request to model generation, assuming it depends based on GPU used and requested video duration and complexities?
Yeah.
And
You're.
we have an answer from Paula, which is also from NVIDIA monitoring the chat, and she says it
Yeah.
depends on GPU and video length, but as a ballpark, short, simple Cosmos video generations take a few to 30 seconds on strong GPUs and up to a few minutes for longer, higher complex, higher resolution videos and clips.
Yep. That's exactly right, Kavan. And so that's sort of this is a great segue into AWS, like because you'll need the appropriate infrastructure, the appropriate kind of way to manage this in order to be able to turn those dials. So I think we're talking about video generation maybe as opposed to model generation. If it was model generation, like fine tuning your own checkpoint, that takes a bit longer. But for video generations, like Paula had said, and then using your AWS infrastructure can help to make that as simple as possible.
Perfect.
Cool. Okay, so
all right.
yeah, let's go over to Nejma.
Perfect. Just before having Najma sharing her screen, you have an audience here, so someone is saying, "Woohoo, go Najma!"
That's
so
awesome.
very
Thanks for
cool.
throwing me
All
that.
right, I just wanted to bring that on.
That's awesome. Okay, yeah, I think we have a perfect segue into running Cosmos on AWS. We've talked a lot about like what is physical AI and this problem of this big data gap and how we can solve this with Cosmos. And I'm sure you guys are starting to itch to know, like, okay, I want to get my hands dirty. I want to start running the Cosmos model. How can I do that? That's where I'm going to walk you through. But before we get into the steps in deploying the model, I want to kind of talk about the architecture so you have an idea of what you're building in the AWS cloud. And like someone mentioned before, it's pretty simple infrastructure. So starting with the big picture, you're going to have your resources set up in a VPC. So that'll be like your isolated network on the AWS cloud. And inside that, you have your two availability zones. And you can think of that as like separate data centers. So if something was to happen and one data center goes down, you still have the other one running, and it's how you ensure resiliency in your design. And then when it comes to actually running the model, what we've chosen is Elastic Kubernetes Service, EKS. That is AWS's fully managed Kubernetes service where you can deploy NIM for Cosmos Predict. And if no one knows what like NIM is, or if you never heard that before, it stands for NVIDIA Inference Microservices. And it's just basically how NVIDIA packages their models for deployment. So you don't have to figure out like, how do I optimize the model or set up the right runtime? Then we'll wrap all that into a ready to go container, and then you can deploy on EKS. And if you're wondering, well, why this service specifically for running Cosmos NIM, the reason is because when you're running Cosmos NIM containers, you really need orchestration. You could theoretically just spin up like an EC2 instance directly, but then you're going to be managing everything yourself when it comes to scaling and availability, or scheduling those workloads across the GPUs. So by using EKS, you're able to have that be completely handled for you. It's fully managed, and you can just not have to worry about the control plane and spending time on that. It'll scale when your demand is spiking, and then it can spin back down. And really that also goes into this idea of total cost of ownership optimization. And I think somebody was mentioning like, somebody had mentioned in the comments something about cost. And what's great with this kind of architecture is that with the pre-optimized NIM containers and then utilizing EKS auto scaling, you're really only paying for what you use.
Yeah.
So again, like resources scale up, then when inference load spikes, and then they can scale back down when it doesn't.
Yeah.
And that's really how you keep your costs in check while still getting really great performance when running these models.
Yeah.
Um,
Also, if you allow me to interrupt you can also have spot instances as worker nodes on EKS, right? So you can
yeah,
have EC2 spot instances, or if you know that you're gonna do this on a predicted scaling, you can get reserved instances as well to auxiliate on the cost for these EC2 instances.
exactly. Yeah, that's a great point. And so really you have a lot of control in how you are running those models and have a lot of insight. And then when it comes to actually storing all that synthetic data that you're generating with Cosmos, that's where Amazon Elastic File System comes in. And then again, going back to understanding what is running and the health of what you're running, that's why we're going to have CloudWatch to monitor that cluster health, inference job performance. Really, you can see what's going on in the cloud. And that's basically the whole stack. You know, you have compute, you have orchestration, storage, monitoring, and it's all managed, it all scales, and really works great together on the AWS cloud. So from here, I'll go ahead and switch over to kind of the demo. So I'm going to go ahead and stop sharing the presentation and start pulling up where you would get the instructions to follow along and actually start deploying this model. And for the sake of time, I'll just kind of go over the instructions instead of actually doing it live, because realistically, running all these steps does take some time and running inference. So I'll just run through the steps and then kind of show you some example outputs so everyone can understand. So where you'll want to start off is going to be in the NVIDIA public repo called NIM deploy. This is going to contain your reference implementations, example documents, architecture guides, and all the steps that you're going to need to be able to deploy NIM on EKS. And if you actually scroll down to deployment options, you can see the different cloud service providers. And down here, we have one for EKS, Managed Kubernetes for AWS. And if you navigate to this page, this is where you'll get all the instructions on actually how to deploy. So one important thing I want to point out with this specific instructions is that it's for a default model or like a default LLM inference. Which works great, it works great for those text models, but we're here, specifically talking about Cosmos, and it's going to have a different GPU requirement. And so as I go through the steps, I'll actually show you where you'll make a few changes to those CDK stacks and the files so that you can specifically deploy for Cosmos. But either way, this repo is going to provide you that VPC, EKS cluster, the storage monitoring, and everything you need to deploy. So starting out, it has like another architecture. I think this is great because it goes a little bit more into detail than what I was showing before. So we can quickly review this one as well. You'll see at the top, there's the application load balancer, and that is going to be sitting in a public subnet. And it's essentially like the front door. So it's how the inference requests come in and they get routed to the right place. And then right below that is that cluster management API server. And that you can think of that kind of like the brain of the operation. So that's going to decide, where the workloads run and manages the clusters and, all the health related to that. And then right next to that is the EKS cluster admin role. And that's simply just to be able to control who manages access to the clusters. And then everything below that is going to be sitting in your private subnet. In there, you're going to be having the reason you have that in the private subnet is just simply because your private subnet doesn't get exposed to the internet, and then everything else will run in there. And you're going to have the auto scaling group that is going to be what allows your clusters to grow and shrink based on demand, like what I was talking about earlier. So one inference or press spike, you can spin up more nodes. When they quiet down, it can also spin back down those resources. The architecture is showing that there's going to be 2 G5X large GPU instances. For Cosmos, we'll be switching those out, which I will be able to show you guys in a second. But essentially, the instances that you're running are like your worker nodes. Each one is running multiple pods, and each of those pods is actually where that NIM container is sitting and where all the inferencing is happening. And then Like I showed in the previous architecture, you can have EFS, so that all the synthetic data that's being generated can land in there, and that's where you would access all those generated data. So that's a basic architecture and flow of everything, and then from there you continue into the infrastructure setup. So before you start, running all those CDK commands, make sure obviously that you have all your dependencies installed. So Docker, Helm, etc. And then you would also clone the repo to your environment. So whatever IDE you want to utilize, make sure you clone your repo, and then you would deploy the 3 stacks in order. And this is going to be where you need to make a little bit of a change so that you can specifically point to Cosmos. So let me pull up that for you guys. So this is my IDE. I went ahead and cloned the repo, and then I went into this specific file, the EKS cluster stack. And you'll want to come in here, and what you want to do is change the instance type from that G5 that is in there by default to that P548X large. So that is going to be what's going to be able to allow you to run Cosmos, because it's a bit of a larger model than what is in default. So this is going to be able to cover everything that you need to run Cosmos. And then you also want to bump up that disk size as well, and then switch out the AMI type, because this is what is compatible with the instance type that we are choosing. So that's a simple thing that you just have to switch out with the stack, so that you'll be able to run it for Cosmos. We can actually go back.
Someone asked, what are the AWS services that are created by this CDK script? That's a CDK script, right?
Yeah, it's basically going to deploy the same things that you're seeing in the architecture.
Architecture. Perfect.
Yeah, exactly. It's going to spin all that up for you. So it saves you a lot of time. You don't have to do that individually in the console. Just deploy that stack, and then all those resources are going to get deployed.
Cool.
So
does it deploy an auto scaling group for the EKS worker?
Yes. Yep. It does that as well. And then you'll be able to have auto scaling, so you don't have to worry about that as well. And then from there, the next step we're going to have is the cluster setup for inference. Also pretty straightforward, just mostly running the command. So install the NVIDIA device plugin, verify that your GPUs are visible, and then one other side step that you'll have to do is create the NGC API key secret. So this is what's gives you access to be able to. I can't recall what this one gives you access to, but it's an important step nonetheless. But you'll come to this website here, and you'll want to actually create an account, and then you'll want to create an access key, and then you'll copy that key into your environment as a variable, and then from there you'll follow that last step, which is creating that running the Docker register secret, and then from there you should be all set up to have the clusters for inference. And then one other quick step that you'll do is set up monitoring, and this just allows monitoring so you can see what your GPUs are doing while you're running, and then you just run these 2 commands. So install the Prometheus stack, and then also install that adapter as well. Cool.
Monitoring, it uses CloudWatch, right, for the metrics, so you can see the CloudWatch metrics regarding.
Yeah.
Do you know if it does the application metrics or just like infrastructure EC2 auto scaling?
That's a great question. I'll have to double check. From what I know, it's going to be really looking at the health of the clusters and the nodes that are running, and like the GPU metrics. So I'll double check that though.
All right. Cool.
And then from there, the last step that you have is just doing your NIM deployment. So you'll want to run the storage setup and then fetch your NIM Helm charts. And those are basically like a package manager for Kubernetes. And this is going to be another step that we'll have to just make some slight changes so that we're pointing to the Cosmos predict model. So once you fetch those Helm chart files, you'll go back into your IDE, pull up the files, and I will show you. So by default, the files are going to be configured for the default LLM that is set up. So you'll want to do is come into here into storage, and these are the default files that you get. And you'll want to make a copy for the NIM cache, NIM service, and the EBS file. And what you'll do is come into this file and make changes so that we are referring specifically to Cosmos. So looking at the repo, you want to change it out to the Cosmos repo. Changed out the model name specifically for Cosmos. Again, bumping up the size because this is a much larger model. And if needed, check here as well that you might need to switch this out to reference the Cosmos service. And then do that for all 3 files as well. So again, just switching this out so that we're specifically pointing to the Cosmos model.
Yeah, someone just mentioned they love to see Hiro in action. That's interesting.
Maybe another live share. I think actually in our series, we're probably going to have another episode where we talked about utilizing Hiro for physical AI, if I'm not wrong, right?
Yeah. That's interesting.
So we'll definitely get a chance to see this, but great service to utilize while you're running these models, trying to debug and figure things out. So highly encourage you to check it out if you have time. But that's the basic changes that you just have to make to those files, and then you'd be able to come back and just continue through and just deploy those Helm files, and then just add apply ingress, and then that's the basic setup for the repo. You have everything ready to go, and you'd be ready to go to your last step, which is to run inference for Cosmos. And so you'll want to go to the API reference documentation. This is going to provide you with the sample commands. So when you're going to generate those video samples, you'd see here we have it for predict, we have it for text to world model or video to world, as well as for Cosmos transfer. And you can essentially just copy this command into your terminal to be able to run an inference. And to give you an idea of like what's happening, so you're providing the model with a prompt, so that's a text description of the scene you want to generate. You can also provide, say, a negative prompt, so things you want the model to avoid in its output. You have the option of, prompt unsampling, making that true or false. So when it's true, Cosmos is essentially using an internal LLM to enhance your prompt, so with additional details before it starts generating. You can control the seed, which controls the reproducibility, guidance scale, which is basically how closely the model follows the prompt that you provide. So making that a higher value means like, okay, you're going to be more strict, adhere to what I am telling you, versus if you make that like a lower number, you're giving the model more creativity and freedom in terms of how it creates. And then as well as some other stuff, you can add your steps, you can change out how the output resolution looks, the total frames to generate, and so on. So you would essentially come here, copy this over to your terminal, and then you can start running inference. And so I'll go back to my slides because I have a video that will show you what the output would look like. Let's go back over there. Okay, there we go. So I can play this video and it should show you what the output should look like. So this is going through the same steps I was kind of just showing you earlier, and how you should, change out. So we're talking about Cosmos specifically. And then when you're ready, you'll go and fetch your prompt. And then you'd go back and feed that into your terminal to be able to run inference, and then you'll be able to get a video output, because both it's text to world is going to be inputting text, getting out a video, versus video to world would be inputting a video and getting out a video as well. And so you can see with the outputs, you inputted a video, you get an output video. With Cosmos Predict, we're generating those predicted future states, versus with Transfer, you're basically augmenting the way that the video environment looks like. So the box colors are different, the color of the table is different. And that's essentially how that goes. I mean, I'm going to move on just talking more about Cosmos in the real world, but I'll take a pause if there's any questions or anything from there.
Yeah, there is someone that said you can try NIM, NVIDIA Inference Microservices models, for free under the NVIDIA Developer Program. So, Brad, after Naj finishes here, if you want to talk a little bit about the NVIDIA Developer Program, just remembering we just have 4 more minutes. But yeah.
Great.
Okay, yeah. So really quick, I know we're almost at time. I just want to kind of talk about how Cosmos looks like in the real world. So here at AWS HQ2, the solutions architect robotics team has actually been utilizing Cosmos for our projects when we've been using humanoids. So we've been using the Cosmos model to augment real world data with synthetic data sets during our policy training for like item pick and place. And the way we've been able to do that was starting with capturing 800 episodes of human teleoperated data of a robot performing pick and place tasks in a single environment. And then that really gave us the ground truth and set the baseline of what successful task completion looks like in the real world. And from there, we then did our second step, which was augmenting the data using Cosmos Transfer so that we can offer variations, like I said before, that materials, the lighting conditions, the table color. And then finally, we use Cosmos Reason to evaluate and filter the quality of that synthetic data. And so this is just one example of the art of possible with Cosmos. With each type of model, there's so much that you can accomplish with them all working together. But the big takeaway that we want you to understand is that you have the capability of compressing months of real world data collection into just hours of synthetic generation. And so with that, I just want to, wrap it all up with everything we've talked about and give you the big picture of, why AWS specifically, why deploy on AWS? And simply put, there's 4 main reasons. First, simplified operations with everything I've been talking about with EKS and not having to manage everything yourself. You really just spend less time on infrastructure and more time on your AI pipelines. And then again, scale. The synthetic generation is, such a compute-hungry task, but with AWS, you can scale across GPU clusters with EKS. You can run jobs in parallel. You can do so much more faster. And then, like I said, costs with our pay-as-you-go pricing model, you really just pay for what you use. You spin up your GPUs when you need them. You scale back down when you're done. And then lastly, it all plugs together with the broader AWS ecosystem, the way that all these services beautifully work together and connect natively. And so, yeah, it's, whether you're getting started with synthetic data or you're already thinking about scaling with physical AI workloads, the art of the possible is endless, posting on AWS. And, with that, we can, wrap it up with some resources if you're interested. And if we have a few minutes, we can go into like the Q&A.
Yeah, we don't. We are 1 minute. So let me just quickly, before I bring Brad, let me share my screen here and just show where we are, what we are doing in this show. So if I can have my screen share on. We are here. We are in the data. We are in the first episode of this series. Next Thursday, we are going to talk about training. So I just wanted to bring that to contextualize where we are, and then we can have Brad talking about to wrap up the NVIDIA Developer Program.
Yeah, so thank you for being here. I think you all know the drill at developer.nvidia.com to get started. And I think we were talking about ability to use the NIMs, which is a great simplifier to run these models and all the dependencies. Use your AWS environment and run those NIMs and EKS, for example, to get started, or SageMaker. So yeah, so that's kind of the path, but get started there. And then I think also we put a bunch of links to our repos in the
Cool.
chat as well. So please use those.
Awesome. Yeah. So thanks everyone for participating, and especially for you on the chat. I am seeing lots of messages here of people that enjoyed watching this. And yes, join the physical AI community on Discord as well on NVIDIA, discord.com/invite/NVIDIA Omniverse. And that's it. We are 1 minute late. Sorry for taking that much of your time. I hope you enjoyed, and see you on the next week with our second episode where we are going to talk about training, also with AWS Solutions Architects and NVIDIA Developer Relations Team. Thank you, and see you on the next week.